Hello and welcome back. In section 5, we go over ordinal logistic regression. More specifically, in this section, we are going to take a look at how to do ordinal logistic regression in R, and then we develop ordinal logistic regression model using significant variables, and we also do interpretation, followed by misclassification error and confusion matrix, and lastly we'll go over prediction and model assessment. So let's start with the ordinal logistic regression with R. In this video, we are going to take a look at CTG data that we had earlier used, and we'll get started by doing data partitioning into training and testing dataset, and then we are going to develop ordinal logistic regression model, and then we'll also do calculation for p-value, which will tell us whether a variable is statistically significant or not. So let's get started by reading this CTG data. So this is on my desktop, and since it has headers in the first row, I'm going to say header equals true, and we can read this in CTG. So once we have read this, we can look at structure of the data. So you can see it has 2126 observation with 22 variables, and as you had seen earlier, this 22nd variable is called NSP, where N stands for normal, S for suspect, and P for pathologic. So these are the three states of a patient, which is determined with the help of a specialist, and these are coded as 1, 2, and 3 in the data set. So although R reads them as integer, but actually they are not integer, and in fact we can say because normal is 1, suspect is 2, and P is 3, pathologic is 3, so there is some order to this. So in terms of health, 3 is the worst condition, and 1, which is healthy, is the best condition, and suspect is in between. So this is the ordinal kind of data where 1 is better than 2 and 2 is better than 3. So that's why we are going to make use of ordinal logistic regression. But before that, we have to convert this into ordinal data. So let's do that in the next line. So in CTG NSP, we want to change this to ordered, as dot ordered. So now if you run this structure for the data set, you can see this last variable NSP is now ordinal variable or ordered with 3 levels, where 1 is less than 2 and 2 is less than 3. Now there is another variable which is tendency, and it takes only 2 values, 0 and 1, and although R says this is integer because it looks at 0 and 1, but in reality this is a factor variable. So what I'm going to do is I'm going to convert tendency into factor. Now again, if you run structure, you'll notice that tendency is now a factor variable. In fact, it has 3 levels. There is a -1 value also. Let's do a cross tabulation, and we are going to do this for NSP, which is an ordinal variable, and tendency, and the data set is called CTG. So if you look at this cross tabulation for NSP versus, if you look at this cross tabulation for NSP versus tendency, you notice that most of the values are more than 5. In fact, lowest value we have is 15. So that means our data is okay for further analysis. If we have any cell which is less than 5, then we need to take some steps to make sure that we don't have values less than 5. So now let's do data partitioning. So we'll store this in, we'll do like independent samples and store this in IND, and our sample size is going to be 2, one for training and one for testing, and we are doing sampling with replacement. So replace equals true, and let's say we want probability to be for training data set 70% and testing data set remaining 30%. Now before we do this, we can also use set.seed. Let's use maybe 333. So if you run this line before this line, so what will happen is we'll have same training and testing data set. So comparisons will be easier. So we can use training where CTG and IND is 1, and after comma nothing means all columns, and testing we have IND equals 2, and again all columns. So 2126 is broken up into two parts now. Training contains 1516 values, testing contains 610 values. So remember that we have used 70% and 30%, but if you do the math, you may not get exactly 70 and 30 split. So it might be slightly more or less. So that doesn't matter because this is done randomly. So now we can do ordinal logistic regression, and we are going to make use of a package called MASS. So I can call this using a library function, but if you do not have it, you will have to install it by going to packages. So within this we have something called POLR, which stands for proportional odds logistic regression, which is in fact another name for ordinal logistic regression. And we want to do NSP versus, let's say, all other variables, and our data set is training, and we should also say HESS equals. So we'll store this in model. So we get some warning, and it says that design appears to be rank deficient, so dropping some coefficients. So generally if we get an error, that's a major problem, but warning, we can still, with warning we are still fine. So let's look at summary. So we can see we get this model with the coefficient estimates. We also have standard errors and t-values, and in fact it may be a good idea to make use of this data to also have p-values, so that we know which variables are significant. So I'm going to do a calculation for p-value, and what we'll do is we do a C table. Coefficients, we'll make use of information from the summary of model that we have created, and in fact we can put a parenthesis to also get a printout of whatever we are doing. So let's run this. So in C table we have this output stored. Now let's create p-values using normal distribution, and we use absolute values, and we make use of C table that we created, all rows, and then we have, let's call this as t-value. Remember we have t-values, and let's say lower tail equals false. We multiply this by 2 and run, and now we can have this C table which will contain, so we can bind the columns using C bind. So C table that we created, and also p-value that we want, and to get simultaneous printout we put the whole thing in parentheses. So we have this complete table where now we also have p-values, and suppose we are interested in 95% statistical confidence level. So that means any p-value which is more than 0.05 is not significant. So those we can take out from the model. So if you look at the first value, it is 3.3 times 10 to the power of -1, which means this is like 0.33. So this means that LB is not statistically significant. So what I'm going to do is, anything that I find not significant, we can indicate that we don't want that in the model. This is almost 0, so this is significant. This is 0.003, so this should be fine. Now we have 0.43, so MSTV will go out. This is quite small, so we can retain this. Now this is 0.03, so 0.03 is less than 0.05, because this is 3.8 times 10 to the power of -2, so this is 0.03, so this is still fine. This also is okay. And then we have Nmax and N zeros, so these two will go out. So these two go out, and then this is 0.02. So again, with 95% confidence, we can keep this. This is 0.06, so we can take out mean. Similarly, median is 0.16, so we can take out median. Variance is fine, this is quite small, 10 to the power of -6. And then tendency, because this one is small, so we can keep tendency. So this is level 1 versus level 2, so 1 is like normal versus suspect, and this is suspect versus pathologic. So now we have indicated which ones we do not want in the model, so we can rerun this model. And in fact, by trial and error, I have also seen that there is a variable in the original data set called max, so that also has some issues. So I'm going to take that out and rerun the model, and you'll notice that now there is no warning error because I have taken out this max. And we can do the summary, p-values, and now if you look at all the variables, you'll find that all the variables are statistically significant. So now we can use this model as our final model. So having calculated p-value and identified what variables are significant, so we have completed all the steps.